Hello student, I am Nirmala Morade, Department of Mathematics, S.V.K.T. College, Devali Camp. In today's lecture, we are going to study what is meant by subspace, one important results related to it, and some examples. So first, let us see what is the definition of subspace. So first consider a vector space. So let V be a vector space. So let W be a non-empty subset of V. W be a non-empty subset of V. This W, a subset of V, is said to be subspace. A non-empty subset W of V is said to be subspace if it itself a vector space with respect to the operation addition and scalar multiplication defined on V. So first we consider V is a vector space, W is a non-empty subset of V. This W is said to be vector space of V. W is said to be subspace of V. Subspace of V if W itself a vector space with respect to the operations addition and scalar multiplication defined on V. So suppose we have to given one vector space, we consider its non-empty subset and we want to show that it is a subspace. Then according to this definition, we want to show that W itself a vector space. So we know that there are 10 properties for a vector space. Now first we recall all these properties here. So we first write all the properties of the vector space or the axioms of the vector space. Consider V is a vector space with two operations, addition and scalar multiplication. So the first property is now we denote the elements of V as a U bar, V bar and W bar, and consider the scalars K and L are the scalars here. We consider these are the scalars. So the first axiom of the vector space is vector addition is closed in V, that is U bar plus V bar belongs to V. Second axiom is addition is commutative, that is U bar plus V bar can be written as V bar plus U bar. Third property is addition is associative, that is U bar plus in bracket V bar plus W bar can be written as U bar plus V bar in one bracket plus W bar. This is the third property. Fourth property is existence of zero vector. So there exists a vector, we denote it by 0 bar, belongs to V such that U bar plus 0 bar is always equals to U bar. This is our fourth property for the vector space. The fifth axiom or the property is existence of negative element. So for any u belongs to V, there exists negative element which is denoted by minus V such that u bar plus minus u bar equals to 0 bar. So for u bar belongs to V, there exists minus u bar again belongs to V such that their addition is equals to 0 bar. This is our the fifth property. Now our sixth property is, now next remaining 5 properties are related to scalar multiplication. So if I consider one scalar, one vector, then this is called the scalar multiplication. It again belongs to V. 7 properties, k plus L times, k and L both are the scalars, u bar is equals to k times u bar plus L times u bar. This is the 7th property. The 8th property is k times u plus v bar can be written as k times u bar plus k times v bar. The 9th property is KL times U bar can be written as K times L U bar. And our last property is, the 10th property is, this is the last property, 1 times U bar is equals to U bar. So these are the axioms or the property for the vector space. Now we know that if W is a subspace of V, if and only if it is itself a vector space with respect to the operation addition and scalar multiplication on defined on V. So suppose I want to prove that W is a vector space. So we want to prove all these 10 properties. For all the members U bar, V bar, W bar belongs to W and KL belongs to V. But among these, certain axioms are inherited from V. So for example, suppose I consider the second axiom. So second axiom is U bar plus V bar equals to V bar plus V bar. If this axiom is true in V, so automatically it is true in W also. So now concentrate here, observe here the second axiom. Next one is the third axiom. Next one is the sixth one, fifth one, 8, 9 and the 10th one. So you can observe that the second, third, that is commutative, associative property, not a sixth one, 7th one, 8, 9 and the 10th one. All these properties are inherited from V. That is, all these properties are true in V, then they are true in its subset also. They are true in its subset. That is, if all these properties are true for the members of V, they are automatically true for its subset, because all the members of the subset again in V. So suppose we want to prove that W is a subspace, then all these property which is marked by correct sign are automatically true. So we need to concentrate here first property, that is closure for addition, next existence of 0, existence of negative element and existence of the close for the scalar multiplication. So now for that we will see one important result, and that result is So this is a theorem related to subspace. A non-empty subset W of a vector space V is a subspace if and only if it is closed for addition, that is U bar plus V bar belongs to W for all U bar and V bar belongs to W, and the second condition is KU belongs to W, that is W is closed for scalar multiplication if K is a scalar and U bar is an element of W. Okay, now let us prove this theorem first. So now consider the first part. So in first part we assume that first we consider V is a vector space and W is its non-empty subset. Suppose it is a subspace. Assume that W is a subspace of V. W is a subspace of V. And we want to prove these two conditions. It is closed for, W is closed for addition and closed for scalar multiplication. Now see, by definition of subspace, if W is a subspace of V, W itself a vector space with respect to the addition and scalar multiplication which are defined on V. And therefore, W satisfy all these 10 axioms for all U, V, W bar belongs to W and K are scalars. So automatically the first condition, obviously the first condition A and B are true because of axiom 1 and 6.1. If W is itself a vector space, then by axiom 1 it is closed for addition and by axiom 6 it is closed for scalar multiplication. So both properties are true here. So both A and B, both conditions are hold here. Now consider the converse. So conversely, suppose W is a subset of a vector space V with these two conditions, that is condition A and condition B. It is closed for addition and closed for scalar multiplication. And we want to prove that W is subspace of V. Prove that W is subspace of V. So according to the definition, to prove that W is a subspace of V, we want to prove that it is itself a vector space, that is we want to prove all these 10 axioms. Okay. So among these 10 axioms, already I told you the axioms 2nd, 3rd, then 7th, 8th, 9th and 10th. All these axioms, see here, axiom 2nd, that is commutative property for addition, associative property for addition, 3rd axiom, then 7th axiom, 8, 9 and 10. So all these properties are inherited from V. All these properties are that is, these properties are true for larger set, they are true for its subsets also. So now it is remain to prove that first, 4th, 5th and 6th property. So first property obviously true because of condition A. The condition A says that if we take two elements from W, their addition is again in W. So first property is true because of condition A. Now next, concentrate on this 6th property. It is true because of condition B. Suppose I take K is a scalar, U bar is a vector in W, then because of condition 2, this product, this scalar multiplication again in W, that is it is closed for the scalar multiplication. So the 6th property is true because of condition 2. So now it is remain to prove that condition 4th and 5th, that is existence of zero element and existence of negative element. So now for that we use the condition B. So concentrate on condition B. Condition B says that a scalar and a vector in W again belongs to W. Again belongs to W. Now we take K scalar is equals to 0. So this product becomes 0 into U bar. Again it is equals to U bar belongs to W. Okay. It is 0 bar. We put k equals to 0, so this product becomes, this scalar multiplication becomes 0 into u bar, which is 0 bar belongs to w. That is, there exists 0 element in w also, or 0 element also belongs to w, and we know that if there is a 0 element in w and we add in any another element, answer is again a 0. So this property is also true, existence of 0 element for w. Now we prove the fifth property, existence of negative element. So for that again we use the same property. Since we know that a scalar k and a vector u, the product again belongs to w because of second condition. Now here we replace k equals to minus 1, scalar k equals to minus 1. So k into minus k u bar becomes minus 1 times u bar, which is equals to minus u bar, again belongs to w. So for u bar belongs to w, minus u bar also belongs to w, that is their negation also belongs to w, and if you add these two elements, u bar plus minus u bar, the answer is equals to 0 bar. Okay, so thus all the 10 axioms are true here, and therefore if these two conditions are fulfilled, then w is itself a vector space, and that's why it is a subspace of V. So remember, this is a very important result for solving the problem. So we just recall this result again. What is the result? The result says that any non-empty subset W of a vector space V is a subspace if it is closed for addition and closed for scalar multiplication. That is, for u bar, all u bar v bar belongs to W, and for k scalar k, u bar plus v bar and k into u bar belongs to W. This is the condition to show that a subset is a subspace. So we have to either we have to show that a subset is a subspace, prove that it is itself a vector space, but that is a very lengthy, because in that case we have to prove all the 10 property. So instead of this, to prove that a non-empty subset is a subspace, we have to only prove the 2 property. It should be closed for addition and closed for the scalar multiplication. So now let us study some examples by using this result. So first example is, now consider V is any vector space and we consider a set containing only the 0 vector of V. So we can easily prove that it is a subspace of V, and it is called the 0 subspace of V. Since there is only one element in set W, so if we define the addition, 0 bar plus 0 bar equals to 0 bar. So it is closed for, W is closed for addition, and if I take any scalar, multiply with the element of W, that is 0 bar, answer is again 0 bar, which is again in W. So W is closed for addition, closed for scalar multiplication, so it is a subspace, and it is called the 0 subspace of V. So for any vector space, if we consider a set containing its 0 element, is always a subspace of that vector space, and it is called the 0 subspace of V, or 0 subspace of that vector space. So this is one of the simplest example of a subspace. Another example is, we consider V is a vector space and take W is equals to V itself. So since W equals to V itself, so it is again itself a vector space, and that's why it is a subspace. So every vector space is a subspace of itself. So remember, these are the two trivial subspaces of any vector space. So third example is, so if we consider any line passing through origin is always a subspace of R2 as well as the R3 also. So suppose we consider any line which is passing through origin is subspace of R2 as well as R3. Geometrically, suppose we consider this is one vector, this is a vector on, we consider two vectors on a straight line. Suppose I consider first vector u bar and second vector on v bar on the same line. And if we do the addition is again in the on the same straight line as well as the scalar multiplication also. So if u bar and v bar have the same direction, they lie on the same line, then their addition is again on the same line. Okay, and for scalar multiplication, suppose this is u bar, then depending on the value of k, whether it is greater than 1 or less than 1, its position depending on the value of k, but it lies on the same straight line. So if u bar is a vector on some line, then k into u bar, any scalar multiplication is again on the same straight line. So it is closed for addition, closed for scalar multiplication. So if I consider any line passing through origin, it is a subspace of R2. Similarly, we can easily prove that it is a subspace of R3 also. So another example is planes passing through the origin. So suppose we consider the planes, any plane passing through origin is a subspace of R3. So geometrically, suppose we consider this is a plane which is passing through origin, and if I consider this is the first vector u bar and this is another vector v bar, these two vectors lie on the same plane which is passing through origin. Geometrically, addition of these two vectors as well as the scalar multiplication of these two vectors again lie on the addition of these two vectors, and another one is the scalar multiplication of any vector which is lie on the same plane again belongs to the same plane. That is, if two vectors belongs to the plane which is passing through origin, then their addition again in the same plane as well as the scalar multiplication also belongs to same plane, and therefore any plane which is passing through origin is a subspace of R3. So we write some subspaces of R3. We just combine all these results. This is a vector space R2. This is a vector space R3. So the first subspace is R2 is a subspace of itself. R3 is also subspace of itself. We write the subspaces of R2 as well as the R3. So first they are itself. Next, zero vector space. Here 0 bar is nothing but 0 bar of R2 is nothing but the ordered pair 0 0. It is a zero subspace of R2, and the zero subspace of R3 is a triplet containing a set containing this triplet only 0 0 0. Next subspaces are any line passing through origin. Lines through origin. Any line passing through origin is subspace of R2, similarly for R3 also. And one more subspaces or another subspaces for R3, any plane passing through any plane passing through origin is also subspace of R3. So R2 and R3 has a infinitely many subspaces because there are infinitely many lines through origin and infinitely many planes for origin. So remember, what are the subspaces for R3? R2 itself, 0 space, and next is any line passing through origin. For R3, the subspaces are R3 itself, next 0 space, next any line passing through origin, and any plane passing through origin is also subspace of R3. So now we consider some examples. By using the theorem, we determine whether the given set is a subspace or not. So determine whether S is subspace of R3 or not. Here S is equals to set of all triplets x, y, z such that ax plus by plus cz equals to 0, where x square plus b square plus c square is not equals to 0, means AB are not simultaneously 0 here. Obviously it is a subset of R3 with this condition, and we check whether S is a subspace of R3 or not. If we consider the geometrical meaning of S, we know that any equation, any linear equation in 3 variable, ax plus by plus cz equals to 0, where ABC are not together, 0 represent a plane passing through origin. So here S geometrically represents S represents a plane passing through origin. It represents a plane passing through origin. So therefore it is a subspace also. Or we can easily prove by using that theorem it is a subspace. So it is a subspace. Now we use the another method to prove that. We use the theorem to prove that it is a subspace. So now for that we take the two elements from S. So let u bar equals to So take these are the two elements from S. U bar equals to x1, y1, z1, v bar equals to x2, y2, z2 are the elements from S. And take one scalar. So okay, we want to prove that it is a subspace, or we check whether it is subspace or not. So if it is closed for addition and closed for scalar multiplication, then it is a subspace of R3. So for that we take these two elements from S and one scalar. Now we consider their addition. So u bar plus v bar. Here operations we use the component wise addition and component wise scalar multiplication. So this is same as x1 plus x2, y1 plus y2, z1 plus z2. Add these elements component wise, x1 plus x2, y1 plus y2, and similarly z1 plus z2. We check whether this is the element of S or not. So since these two are the elements of S, u bar and v bar are the elements of S, so they satisfy this condition. So we get here ax1 plus by1 plus cz1 is equals to 0, as well as here ax2 plus by2 plus cz2 is equals to 0. Now we add these two equations. So add left hand side to the left hand side and right hand side to the right hand side. So adding these two equation, just add these two. So we get here ax1 plus by1 plus cz1 plus, at this side, ax2 plus by2 plus cz2 is equals to 0 plus 0. Now we combine here term, similar terms. We combine the term of a's, b's and c's. So this can be written as a times x1 plus x2 by combine this first and the fourth term. Now combine the term of b's. So from these two terms we can take b common. So remaining terms are, first is y1 and this is the y2, and from the remaining terms we can take c as a common. So remaining are z1 and z2. So z1 plus z2 is equals to 0. So we can observe that this triplet x1 plus x2, y1 plus y2 and z1 plus z2. So this triplet satisfy this equation ax plus by plus cz equals to 0. So this is the member of S. That is here u plus v. This is nothing but u plus v. So u plus v belongs to S here. So S is closed for addition. If we take two elements from S, their addition is again in S. Okay. So now we check the second condition whether scalar multiplication is closed or not. So for that I denote this equation by 1. Just denote this equation by 1. And now we multiply this equation by a scalar k. So this equation becomes k times ax1 plus k times by1 plus k times cz1 is equals to k times 0. So just rearrange the terms. All the numbers, all the variables are here real numbers. So they can be, this can be written as a times kx1. I put k and x1 in one bracket. Actually we use here the associative as well as the commutative property of the real numbers. So without loss of generality, this term can be written in this form, plus b times ky1 plus c times kz1 is equals to 0. So you can observe that this triplet kx1, ky1 and kz1, this triplet satisfies the equation ax plus by plus cz equals to 0. That is, this triplet belongs to S. Okay, this is nothing but k u bar, because if I take k common, this can be written as k x1 y1 z1 belongs to S. That is, k u bar belongs to S. That is, S is closed for the scalar multiplication. So S is closed for scalar multiplication as well as the addition of two vectors. So it is a subspace. So you can write geometrically also, or we can show that this is a subspace by using this method. So always remember, I recall it again. S is the set of all triplet x, y, z such that ax plus by plus cz equals to 0 with this condition, that is a, b, c are not simultaneously 0 here. Obviously it is, first of all, it is a subspace of R3. Geometrically it represents a plane passing through the origin. So it is a subspace. This is one way to write the answer of this, or the another way we can go for this procedure. Take two elements from S and show that their addition is again in S and scalar multiplication is again in S. So same method can be used for the line passing through the origin. So if I consider this equation, this set of all x, y such that ax plus by equals to 0 with the condition a square plus b square not equals to 0. It represents a straight line. It represents a straight line in R2, and here a and b are not simultaneously 0. It is also represent a subspace of R2. So use another method to show that it is a subspace. That is, use the theorem. Take two elements from S and show that they are closed for addition and closed for scalar multiplication. And remember one more thing is, if S is a subspace, then it is closed for addition and closed for scalar multiplication. Suppose one of the condition is not true, either it is not closed for addition or not closed for scalar multiplication, then it is not a subspace. So for that we will see one example here. So take C, V is equals to R3. S is the set of all vectors of the form A11. Here A is a real number. So we check whether it is a subspace or not. For that we check whether it is closed for addition or closed for scalar multiplication. So for that I consider one element from S. So suppose I consider the element as it is 1, 1. This is U bar. And take k is equals to 2 here. So remember, it is a set of all vectors of all the vectors of R3 of the form a comma 1 comma 1. That is, the last two coordinates y and z are constant here, which is 1 1. So we take u bar. Obviously it is from S. Take k is equals to 2. Now calculate k into u bar. So we consider 2 1 1. So which is same as 2 times a, it is 2, it is 2. This vector not belongs to S. Why it is not belongs to S? Because now here this triplet is not in S, because here the y coordinate is 2 as well as the z coordinate is also 2. If one of the coordinate is any one other than 1 1, then it is not the element of S. It is not closed for scalar multiplication. Therefore, it is not a subspace of R3. So, if one of the condition is not fulfilled, then it is not a subspace. Today we stop here. In next lecture, we will consider more examples related to it and more vector spaces. Thank you.